Hello, this is section 1.1, Review of Functions. So, let's talk about functions. To define functions, first we will talk about relations. A relation is any set of ordered pairs. To understand this, let's see a few examples. So, a relation is a set, and to describe sets in math, we use braces. Then, inside the braces, we write the objects that belong to this set. In our case, the set is made out of ordered pairs. So, in our example, inside the braces, we will have ordered pairs of numbers. And each of these pairs, we will write them in parentheses. For example, the first one could be 7, 3. Another one could be 8, 1. Another one could be 4, -2. Once we are done, we will close the braces. Each of these pairs in the rectangular coordinate system represent points, and the first number represents the x-coordinate and the second one represents the y-coordinate. All the first values in each of these pairs make the domain of this relation, and all the second numbers represent the range. So the domain has the numbers 7, 8, and 4, and the range has the numbers 3, 1, and -2. Now let's see another example of a relation. We will start the braces, and then inside we will have the following pairs: 1, -5, 2, 4, 2, 11, and one more 9, 0. In this relation, the domain is 1, 2, 2, and 9, and if we have numbers that repeat, we can just list them once. And the range is -5, 4, 11, and 0. So again, the domain is 1, 2, and 9, and the range is -5, 4, 11, and 0. Now, let's talk about functions, and let's see what functions have to do with these relations. A function is a correspondence from the first set, called the domain, to the second set, called the range, such that each element from the domain corresponds to exactly one element in the range. So, this definition tells us that a function is a relation that has specific conditions. And that is that each number from the domain has to correspond to exactly one number in the range. Let's take a look at the first relation we have here. In this relation, we can say that 7 corresponds to 3, 8 corresponds to 1, and 4 corresponds to -2. It is true that each number from the domain corresponds to exactly one number in the range. Therefore, we can say that this relation represents a function. Now, if we look at the second relation, 1 corresponds to -5, 2 corresponds to 4, and we see 2 again that corresponds to 11. So here we have a problem. Each number from the domain has to have only one number in the range, but we see that 2 has 4 and has 11. Therefore, this relation is not a function. So, to see if a relation represents a function or not, we have to look at the domain and see if we have any numbers that repeat in the domain. Like in the second case, we have 2 and another 2. Then we can say that this relation is not a function. Now, most of the times when we see functions, we may not necessarily see them in form of a relation. Instead, we may see them as equations. And just like with relations, not all the equations represent functions. Let's see some examples of equations that represent functions and some that don't represent functions. We will start with the equation y equals x squared. And you will see that this equation represents a function. In this equation, we will assign values to x and we will find y, then we will graph this equation. We will start by drawing a table for the values of x and y. In this table, we will choose the following values for x: -3, -2, -1, 0, 1, 2, and 3. Then, if we raise each of these numbers to the second power, we will get 9, 4, 1, 0, 1, 4, and 9. Now, we know that the values of x are part of the domain of this equation, and the values of y are part of the range. We see that in the range there are some numbers that repeat, but in the domain, all the numbers are different. There is nothing that repeats in the domain. In other words, each time we replace x with a number, we get only one answer. Then, this equation represents a function. Now, let's graph this function. First, we will plot the points. Then, we will connect them. So, here we have the graph of the function y equals x squared. Now, I will show you an example of an equation that is not a function. And that is x equals y squared. Let's create a table of values for x and y. Now, if we look at this equation, we get x by raising y to the second power. And we know that when we raise a number to the second power, the result could be 0 or positive. So, in place of x, we can't use any negative numbers. The smallest number that we can have for x will be 0. So, when x is 0, y is also 0, because 0 to the second power is 0. Now, let x be positive 1. So, what number do we raise to the second power and we get 1? This number could be 1 or it could be negative 1. So, when x is 1, y is 1, or when x is 1, y could be negative 1. Now, you see the problem that we have now. We start seeing numbers that repeat in the domain. But let's continue with the table. Let x be 4. So, what number do we raise to the second power and we get 4? That could be 2, or for the same 4, we could have negative 2. And what if x is 9? Then y could be 3, or y could be negative 3. So, as we see, in the domain we have multiple numbers that repeat. Therefore, this equation is not a function. Now, once we have the points, let's make the graph too. We will plot the points, and now we will connect them. So here we had two equations, and the one to the left represents a function, and the one to the right does not represent a function. You may also recall that we can determine if a graph represents the graph of a function by using the vertical line test. The vertical line test tells us that if we draw a vertical line over a graph and that line crosses the graph just once, then that graph represents the graph of a function. If we draw a vertical line over the graph to the left, then we will see that this line crosses the graph just once. Therefore, this graph is the graph of a function. But if a vertical line crosses the graph more than once, then the graph does not represent a function. In the graph to the right, if we draw a vertical line, we see that this line crosses the graph twice, so this graph does not represent a function. Now, let's see how we can find the domain and the range of a function using the graph. Let's say we have the function y equals x squared plus 1. The graph of this function is a parabola that opens upward and it crosses the y-axis at 1. So here we have the graph, and now let's see how we can find the domain and the range. To find the domain, we have to understand how far this graph stretches to the left and how far stretches to the right. The left branch goes up and to the left indefinitely, and the right branch goes up and to the right indefinitely. So we can say that horizontally the graph stretches from negative infinity to positive infinity. So the domain is the interval from negative infinity to positive infinity. To find the range, we have to understand how far the graph goes down and how far it goes up. The lowest point of this graph is 1. However, the graph goes up to positive infinity. So to write the interval that represents the range, we will start with a bracket to show that 1 is included, it's part of the graph, and then positive infinity. So now we have both the domain and the range. Let's see another example. Y equals square root of x minus 4. Let's start the graph. The lowest value we could use for x will be positive 4, otherwise we would get negatives inside the square root. And when x is 4, y is 0. So this is the first point. Let's choose a few more points. When x is 5, 5 minus 4 is 1, and square root of 1 is 1. So the next point will be 5, 1. Now let x be 8. 8 minus 4 is 4, square root of 4 is 2. So when x is 8, y will be 2. And now this is the graph we get. So now let's see how we can get the domain and the range from this graph. If we need to find the domain, we have to see how far this graph stretches to the left and how far stretches to the right. We see that on the x-axis the graph starts at 4 and goes to the right indefinitely. Then the interval that represents the domain will be brackets, because we want to show that 4 is included, comma, infinity, parentheses. Now to find the range, we have to see how far down the graph goes and how far up. This graph does not go below the x-axis, so the lowest point is 0, and then the graph goes up to positive infinity. So the range is brackets, 0, comma, infinity, parentheses. And now let's see one more example. Let's say we have the function y equals 2x minus 3. We know that the graph of this equation will represent a straight line. The y-intercept is negative 3 and the slope is 2 over 1. So from this point we will go 2 units up and 1 to the right and have another point. Then we will connect these 2 points and we will get the graph. Now let's find the domain and the range. These arrows tell us that the graph will go indefinitely left and right and up and down. Therefore, both the domain and the range will be negative infinity to positive infinity. Next, we will talk about composite functions. Given two functions f and g, the composite function f of g is defined by the composition of f and g of x equals f of g of x. It is evaluated in 2 steps, y equals f of u, where u equals g of x. The domain of f of g consists of all x in the domain of g, such that u equals g of x in the domain of f. I will show you through a few examples how the composition of 2 functions works. So here we have 2 functions. The first one is f of x equals 2x plus 7, and the second one, g of x equals 3x minus 5. First, we will find the composition of f and g of x. When we write the composition of 2 functions, it is important what function we write first, because the function that we write first is the main function and the second one becomes the domain of the first one. So in this example, f is first and f is 2x plus 7. Then to perform the composition of f and g, in this function that is the main function, we will replace this x with 3x minus 5. So we will bring 2 down. Then in place of x, we will write 3x minus 5, then we will bring down plus 7. So all this equals to 2. In place of x, we will write the g function, 3x minus 5, then plus 7. We can also simplify this and get 6x minus 10 plus 7, which is 6x minus 3. Now let's see what we get if we perform the composition of g and then f. Now g is the main function and f becomes the domain of g. This means that in this g function we will replace this x with 2x plus 7. So let's bring down 3, and then in place of x we will write 2x plus 7, then minus 5. We will simplify this as well, and we will get 6x plus 21 minus 5 equals 6x plus 16. We can also find the composition of 3 or more functions, and we can also have the composition of the same function repeating multiple times. So let's see how we could perform the composition of f and f. This means that in the f function, we will replace this x with 2x plus 7. So then, let's bring down 2, and then in place of x we will write 2x plus 7, then we will bring down plus 7. Let's simplify, and we will have 4x plus 14 plus 7, which makes 4x plus 21. Now let's see a few examples from the textbook. We will start with exercise 26 on page 10. Here we are given the function f of x equals x squared minus 4, and we have to find f of p squared. You see how x is replaced with p squared. That means that in this function we have to replace this x with p squared. So in place of x we will write p squared, and all this we will square, and then minus 4. All this equals p to the power of 4 minus 4. In this case, these two exponents are multiplied and we get the exponent 4. Next, we will do exercise 33 on page 10. Here we are given the function f of x equals 1 over x minus 3, and we have to find the composition of f and f. As you noticed by now, there is two ways to write the composition of two functions. We can write it as f of x, or we can write it as the composition of f and f of x. And up here we have the first notation. Now, in our example, the composition of f and f means that in this function we have to replace x with 1 over x minus 3. So then, let's start the fraction, have 1 in the numerator, and then in place of x, write the fraction 1 over x minus 3, and then bring down minus 3. So again, what happened here, we replaced this x with the entire function 1 over x minus 3. So this is the composition of these two functions, but now we have to simplify it because it is a complex fraction and it needs to be simplified. Now let me show you one method of simplifying complex fractions. We will take a look at the numerator of this fraction and then at the denominator of this fraction. In the numerator, we just have a whole number, but in the denominator, we have a fraction and we have another number. So the only fraction in the numerator or in the denominator is 1 over x minus 3. The denominator of this fraction is x minus 3. From here, we will multiply the numerator and the denominator by the denominator of this fraction. So again, we will multiply the numerator by x minus 3 and the denominator by x minus 3. In the numerator, 1 times x minus 3 is x minus 3, and in the denominator, when we multiply 1 over x minus 3 times x minus 3, x minus 3 and x minus 3 will cancel, and we will just have 1. So let's bring down 1. And now we have to multiply negative 3 times x minus 3. Negative 3 times x is negative 3x, and negative 3 times negative 3 is positive 9. So do you see how we don't have a fraction anymore in the denominator? Now we can just simplify this and get x minus 3 over negative 3x plus 10. And this is the composition of f and f. Next, we will do exercise 37 on page 10. Here we are given the function f of x equals x cubed minus 5 to the power of 10, and we have to find possible choices for the outer and inner functions f and g such that the given function h equals the composition of f and g. Then we have to give the domain of h. First, we need to understand the requirements of this problem. The h function represents the result of the composition of two functions f and g. There are multiple functions whose composition gives us x to the power of 3 minus 5 all to the power of 10. We have to provide just one of these possibilities. One easy solution is the following. We have an expression that is raised to the power of 10. This expression is inside the parentheses, and it can represent the inner function g of x. So g of x will be x to the power of 3 minus 5. Now, what do we have to do with this function? To get this expression, we have to raise it to the power of 10. Therefore, the main function f of x will be x to the power of 10. Now, do you see that if I write the composition of f and g, then this function x cubed minus 5 will be moved into this x, and we will have x to the power of 3 minus 5 all to the power of 10. So we can say that the composition of f and g is x to the power of 3 minus 5 all to the power of 10, which is h of x. So the possible choices for f and g are f of x equals x to the power of 10 and g of x equals x cubed minus 5. Now, because g represents a polynomial and f is also a polynomial, then the domain of the h function will be any number from positive infinity to negative infinity. In exercise 45, page 10, we are given three functions. Uppercase g of x equals 1 over x minus 2, lowercase g of x equals x squared minus 4, and f of x equals absolute value of x. We will find the composition of g and f. If we look at the order of these functions, then we can say that f becomes the domain of g and g becomes the domain of this g. This means that absolute value of x will go in place of this x, then this expression will go in place of this x. Now, to find the composition, we can also rewrite this as g of f of x. The part inside the parenthesis tells us that we have to take this absolute value of x and move into this x. So we will bring down g, then in parenthesis, in place of x, we will write absolute value of x squared minus 4. Now, because the exponent 2 makes a number positive anyway, we can remove the absolute value, and this will be the same as x squared minus 4. Now, this tells us that in the g function, we have to replace x with x squared minus 4. So this will be equal to 1 over x squared minus 4 and then minus 2. Then the final result will be 1 over x squared minus 6. In exercise 51, we are given the function g of x equals x squared plus 3, and we are also given the composition of f and g, which is x to the power of 4 plus 6x squared plus 9. We have to find f of x. If we look at this composition, we see that f is first. That means f is the main function and g is the domain of f. So, what has to be done to this binomial to get this trinomial? You may recall the following formula from algebra. A plus b to the second power equals a squared plus 2ab plus b squared. So here we see that if we raise a binomial to the second power, we will get a trinomial. Then, if this formula was applied in our problem, then f of x must be x squared. Now let's check the work and see if all this is correct. So we have that f of x equals x squared, and we have that g of x is x to the power of 2 plus 3. We have to find the composition of f and g. So if f is the main function, g is the domain of f. This means that the expression x squared plus 3 will be moved in place of this x. Then we will have x squared plus 3 all to the second power. Then, according to the formula to the right, x squared to the second power is x to the power of 4. Then x squared times 3 is 3x squared, and then doubled will be 6x squared. Then 3 to the second power is 9. And this is exactly what we have here. So then, in this case, we can say that f of x equals x squared. On exercise 54 on page 10, we are given that g of x equals x squared plus 3. The composition of g and a function f equals x to the power of 2 over 3 plus 3. We have to find the function f of x. So again, what we have here, we have two functions. One of them is unknown, but the composition of them is x to the power of 2 over 3 plus 3. And as you see here, g is first and then f. So g is the main function and f is the domain of g. Let's write again g of x. This is going to be the main function. Then what should f of x be? That when we replace this function in this x, we will get x to the power of 2 over 3 plus 3. Do you recognize that this would be x to the power of 1 over 3? So if we take the composition of g and f, that means we replace x with x to the power of 1 over 3. We raise this to the power of 2 and we add 3. But x to the power of 1/3 to the second power is x to the power of 2 over 3, then plus 3. So we can say that indeed f of x has to be x to the power of 1 over 3. And this will be the answer. Now let's see the following example. We are given f of x equals x to the power of 2 plus 3, and we have to find f of 5 plus h minus f of 5 over h. So the expression that we have to evaluate represents a fraction, and in the numerator, first we will work on evaluating f of 5 plus h. That is, in the function we are given, we are going to replace this x with 5 plus h. So we will have 5 plus h squared plus 3. That is what we will write. 5 plus h squared plus 3. Next we will bring down the negative sign. Then we will evaluate f of 5. This means that in this function we will replace x with 5. Let's start a parenthesis because we have a negative in front and write 5 squared plus 3. All this is divided by h. Now we need to simplify this expression. To raise 5 plus h to the second power, we will use the formula a plus b to the second power equals a squared plus 2ab plus b squared. So then, in the numerator, 5 to the second power is 25. 5 times h is 5h, doubled is 10h. H to the second power. Then we will bring down plus 3. And then in parentheses, 5 squared is 25 plus 3, 28. All this will be divided by h. In the numerator, 25 plus 3 is 28, minus 28 is 0. So we will cross all these numbers. Then out of these two terms, we will factor out h, and then we will cancel with the h in the denominator. So we will have h times 10 plus h over h. H and h will cancel, and the result will be 10 plus h. Or if you want, h plus 10. Next, we will talk about secant lines and the difference quotient. Let's start by reviewing the slope of a line. Given 2 points x1, y1 and x2, y2, the slope is change in y over change in x, or y2 minus y1 over x2 minus x1. Let's see a few examples. Here we have a line and 2 points that belong to this line, and we can find the slope of this line using these 2 points and this formula, or we can find the slope by using the graph. We will start with one of the points, let's say this one, and we will move 2 units up, and this is going to be change in y, and 1 unit to the right, and this will be change in x. Then the slope is 2 over 1, or just 2. In the next example, we have a line that crosses the points -1, 3 and 2, -1. If from this point we move 4 units down and 3 units to the right, then we can say that the slope is -4 over 3. In the next example, there is no change in y, but there is a change in x of 3 units. Then 0 divided by 3 will give us the slope 0. And in the last example, if we start with this point, there is a change in y of 4 units and there is no change in x. Then 4 divided by 0 is undefined. So what we need to know from here that if a line goes up as we move from left to right, then the slope will be positive. If a line goes down as we move from left to right, the slope will be negative. A horizontal line has the slope 0 and a vertical line has the slope undefined. Now let's talk about a few other definitions. A secant line is a line that crosses a curve at 2 points, and a tangent line is a line that touches a curve at 1 point. Now let's consider the following graph. So here we have a curve f of x, and on this curve we have 2 points. One point is P and the other one is Q. Point P has the coordinates x and f of x. So if from this point we draw a perpendicular down to the x-axis, then here we will have x, and if we draw a perpendicular to the y-axis, then here we will have f of x. We will do the same with the point Q. We will draw a perpendicular to the x-axis and the other one to the y-axis. The x-coordinate of point Q is at a certain distance h from the point x. Then x plus h will make the x-coordinate x plus h. Then the y-coordinate will be f of x plus h. Now let's draw a secant line that passes through these 2 points. And now once we have the secant line and the 2 points that belong to this line, we can find the slope. So one point has the coordinates x and f of x, and the other one has the coordinates x plus h and f of x plus h. Then the slope of the secant line, which is y2 minus y1 over x2 minus x1, will be f of x plus h minus f of x over x plus h minus x. In the denominator, x and negative x will cancel, and we will get that the slope of the secant line equals f of x plus h minus f of x over h. Now, this slope formula is also called the difference quotient. Next, we will have a few examples where we will use this formula. On exercise 57, page 11, we are given the function f of x equals x squared. We have to simplify the difference quotient using this function. So let's start with the first part of the numerator, and that is f of x plus h. In this part, we need to replace this x with x plus h. So this equals fraction bar, in the numerator, in place of x, we will have x plus h all squared. We will bring down the minus, and now we will replace f of x with x squared. So, minus x squared all divided by h. In the numerator, we will remove the parentheses. X plus h to the second power is x squared plus 2xh plus h squared, and then minus x squared, all this divided by h. In the numerator, x squared and x squared will cancel. In these two terms, we will factor out h. So we will have h, parenthesis, 2x plus h divided by h. H and h will cancel, and the result will be 2x plus h. Next, we will do exercise 61 on page 11. We are given the function f of x equals x over x plus 1, and we have to simplify this difference quotient. For this part, we will replace this x and this x with x plus h. So let's start a fraction. And in the numerator, we will start the fraction of the function f of x. In the numerator, we will have x plus h, and in the denominator, x plus h and plus 1. Minus. Now we will replace f of x with x over x plus 1. So let's start another fraction and write x over x plus 1. In the denominator, we have h. What we have here now is a complex fraction, and we have to simplify it. The numerator has two fractions, and one has the denominator of x plus h plus 1, and the other one has the denominator of x plus 1. The least common denominator will be x plus h plus 1 multiplied by x plus 1. To simplify this entire expression, we have to multiply the numerator and the denominator by the least common denominator of these two fractions. And that is x plus h plus 1 multiplied by x plus 1. And we will do the same to the denominator. In the numerator, we will use the distributive property, and we will multiply this expression by the first fraction and then by the second one. When we multiply it by the first fraction, x plus h plus 1 and x plus h plus 1 will cancel. And let's start a fraction. And in the numerator, so far we will have x plus h that has to be multiplied by x plus 1. And now when we multiply this expression by the second fraction, x plus 1 and x plus 1 will cancel, and we will have minus x times x plus h plus 1. So we will write minus x times x plus h plus 1. In the denominator, we have h times x plus h plus 1 multiplied by x plus 1. Let's use the FOIL and the distributive property to remove all the parentheses in the numerator. So x times x is x squared, x times 1 is x, h times x is hx, h times 1 is h, then minus x squared, minus xh, and minus x. And let's keep the denominator as it is for now. Now, in the numerator, a lot of things will cancel. X squared and negative x squared, hx and negative hx, x and negative x. Also, h in the numerator will cancel with h in the denominator, and now the numerator is 1. Then the expression will become 1 over x plus h plus 1 times x plus 1. And now we will do exercise 63 on the same page. Here we are given the function f of x equals x cubed minus 2x, and we will simplify the difference quotient f of x minus f of a over x minus a. So here if we have one point with the coordinates a and f of a, and the other one with the coordinates x and f of x, then this expression will represent the slope of the line that passes through these 2 points. First, in the numerator, we will replace f of x with x cubed minus 2x. Then we will replace f of a with a cubed minus 2a. So all this equals to x cubed minus 2x minus, let's start parentheses, and then we will write a cubed minus 2a. In the denominator, we will bring down x minus a. In the numerator, we will remove the parentheses, and we will have x cubed minus 2x minus a cubed plus 2a over x minus a. So far, in the numerator, there is nothing that we can cancel, and if there is a way to simplify this expression, then it should be by factoring. The numerator has 4 terms, so let's see if grouping will work. We will group together x cubed with negative a cubed, then negative 2x with 2a. So let's write x cubed, then next to it we will write minus a cubed, then the rest, minus 2x plus 2a. All this over x minus a. So again, this is one group, and this is another group. Now let's have more space to the right because I want to show you what formula we will use. For binomials, there is a formula that is called the difference of 2 perfect cubes, and that is a cubed minus b cubed, and this binomial can be factored as a minus b times a squared plus ab plus b squared. We will use this formula to factor this binomial. So then, this binomial will be factored as x minus a times x squared plus ax plus a squared. In the second group, we will just factor out negative 2. So we will continue with negative 2, then in parentheses we will have x minus a. All this over x minus a. And now in both these expressions we got x minus a, and this is the common factor. We will factor it out, x minus a, then in parentheses we will have x squared plus ax plus a squared minus 2, all over x minus a. And now x minus a will cancel, and the final result will be x squared plus ax plus a squared minus 2. Now we will do exercise 67 on page 11. In this exercise, a function and an interval of its independent variable are given. The endpoints of the interval are associated with the points p and q on the graph of the function. Sketch a graph for the function and the secant line passing through p and q, and find the slope of the secant line in part A and interpret your answer in terms of an average rate of change over the interval. So the problem is, after t seconds, an object dropped from rest falls a distance d that equals to 16t squared, where d is measured in feet and t is any number from 2 to 5. So this is the function, and we will start by sketching the graph. For t, we will choose numbers from 2 to 5. So here we have the table, and for t, I chose 2, 3, 4, and 5. Each of these numbers will be replaced in this function. So 16 times 2 to the power of 2 will be 64. 16 times 3 to the power of 2 will be 144. 16 times 4 to the power of 2 will be 256. And 16 times 5 to the power of 2 will be 400. Now we will plot the points and we will connect them to get the graph. On the horizontal axis we have the numbers up to 5, and on the vertical up to 400. Now I will plot the points, and now let's connect them. Although the graph of this function represents a parabola, we need the part of the graph for t from 2 to 5. And now let one of the endpoints be point P and the other one point Q. We will draw the secant line through these 2 points and then we will find the slope. For the slope, let's use the point P with the coordinates 2, 64 and point Q with the coordinates 5 and 400. Then m equals y2 minus y1 over x2 minus x1, or 400 minus 64 over 5 minus 2. Then m will be equal to 112. So you see, this function d equals 16t squared tells us about the distance an object falls after t seconds. For example, after 2 seconds the object fell 64 feet, or after 4 seconds the object fell 256 feet. And what we found here is the average rate of change from 2 to 5. These are 112 feet per second, and this means that on average the object falls 112 feet every second. Now let's talk about symmetry in graphs. The first definition is a graph is symmetric with respect to the y-axis if whenever the point xy is on the graph, the point negative xy is also on the graph. This property means that the graph is unchanged when reflected across the y-axis. Let's see an example. So here we have a graph, and let's say on this graph we have a point xy. Then the point negative xy is also on this graph. So again, what we have here, we have a graph that is symmetric with respect to the y-axis. Now let's see the second definition. A graph is symmetric with respect to the x-axis if whenever the point xy is on the graph, the point x negative y is also on the graph. This property means that the graph is unchanged when reflected across the x-axis. Now let's see an example of such a graph. So here we have the graph, and if this graph contains the point x, y, then the point x negative y will also be on this graph. Also, notice that the graph to the left represents a function and the graph to the right does not represent a function. And now let's see the third definition. A graph is symmetric with respect to the origin if whenever the point xy is on the graph, the point negative x and negative y is also on the graph. Symmetry about both the x and the y-axis implies symmetry about the origin, but not vice versa. Let's see an example. So here we have a graph that is going to be symmetric with respect to the origin, and that means that if we have a point on this graph with the coordinates x and y, then the point with the coordinates negative x and negative y will also be on this graph. Now let's talk about symmetry in functions. An even function f has the property that f of negative x equals f of x for all x in the domain. The graph of an even function is symmetric about the y-axis. An odd function f has the property that f of negative x equals negative f of x for all x in the domain. The graph of an odd function is symmetric about the origin. So, functions can be even, odd, or neither. We will do some examples and we will see how to determine if a function is even, odd, or neither. But before we do that, let's practice a little on using exponents on negative numbers. Let's say we have a variable x. If this variable x is replaced with negative x, then of course we will get negative x. Now let's have the expression x squared. In this expression, if we replace x with negative x, then we will have negative x to the second power. As you see, when we replace x with negative x, that negative x has to be in parentheses. And what this means that we have a negative x times another negative x, which makes positive x squared. So what we can say here that if we had x squared and we replaced this x with negative x, the result is still x squared. Now let's have the expression x to the power of 3. In this case, if we replace x with negative x, we will have in parentheses negative x to the power of 3, which makes negative x times negative x times negative x. Negative times negative times negative will be negative x to the power of 3. So in this case, when we replace x with negative x, the result will be negative. Let's continue with x to the power of 4. So we will replace x with negative x, and we will have negative x times negative x times negative x and times negative x. The result here will be positive x to the power of 4. So in this case, when we replace x with negative x, the result is still x to the power of 4. So what we need to understand here that when we have x raised to an even exponent, like 2 or 4, and we replace this x with negative x, the result will still be the same. But when the exponent is odd and we replace this x with negative x, then we get negative x to the power of 3. So if this makes sense, let's start the first example. We are given the function f of x equals 5x to the power of 4 minus 2x to the power of 2 plus 3. And we have to determine if this function is even, odd, or neither. In either case, we always start by replacing x with negative x. So each x in this function will be replaced with negative x. And we will get 5 negative x to the power of 4 minus 2 times negative x to the power of 2 plus 3. Then f of negative x equals, and here we know that negative x to the power of 4 is positive x to the power of 4 times 5 will be 5x to the power of 4 minus 2, and then negative x to the power of 2 is positive x to the power of 2, and then we will bring down 3. So this is what we get when we replace x with negative x. Now let's compare this result with the initial function. If we look at these two functions, and if nothing changed compared to the initial function, then this function is even. As you see, in both cases we have 5x to the power of 4 minus 2x squared plus 3, just like this one. Now let's see another example. F of x equals 4x to the power of 3 minus x. We will determine if this function is even, odd, or neither. And for this, we will start by replacing x with negative x. That will give us 4 times negative x to the power of 3 minus negative x. Then f of negative x equals, and here we know that negative x to the power of 3 is negative x to the power of 3 times 4 will give us negative 4x to the power of 3, and then minus negative x makes plus x. And this is what we get when we replace x with negative x. Now let's take a look at the initial function. The initial function had two terms. The first one was positive and the second one was negative. And now if we look at the result, we see that the first term has a negative and the second term has a positive. So if this function represents a polynomial, and when we replace x with negative x, every single term changes the sign, then this function is odd. And now let's see another example. F of x equals 3x to the power of 5 plus 2x to the power of 3 plus 7. We will start by replacing x with negative x. This will give us 3 times negative x to the power of 5 plus 2 times negative x to the power of 3 plus 7. Then f of negative x equals negative x to the power of 5 is negative x to the power of 5 times 3 will be negative 3 x to the power of 5, and then negative x to the power of 3 is negative, so we will have negative 2 x to the power of 3 and then plus 7. Now let's compare what we got here with the initial function. The initial function has 3 terms and all of them have a positive sign in front. However, when we replaced x with negative x, some of these terms changed the sign, but some of them didn't. Then such a function is neither odd nor even. So now let's review again these 3 examples. If in a function we replace x with negative x and nothing changes in the function is even. If in a function x is replaced with negative x and all the terms change the sign, the function is odd. But if we have a function and we replace x with negative x and some terms change the sign but some of them don't, then the function is neither odd nor even. Also, in all these 3 examples, for simplicity, I picked polynomial functions. If we have functions that are not polynomial, then determining if a function is even or odd may be a little bit more challenging in some cases. And it is also important to mention that if a function is even, then the graph is symmetric with respect to the y-axis, and if a function is odd, then the graph is symmetric with respect to the origin. Now we will do a few exercises from the textbook. In exercise 71, page 11, we are given the function f of x equals x to the power of 4 plus 5x squared minus 12. We have to determine if this equation is symmetric about the x-axis, the y-axis, or the origin. We will start by replacing x with negative x. That will give us negative x to the power of 4 plus 5 times negative x to the power of 2 minus 12. Then f of negative x equals positive x to the power of 4 plus 5 x to the power of 2 minus 12. As we compare the result with the initial function, we see that nothing changed. That means that this function is an even function. And an even function is symmetric about the y-axis. Now we will do exercise 74. Here f of x equals 2 times absolute value of x. Let's replace x with negative x. This will give us 2 absolute value of negative x. We know that absolute value makes a number positive, and having absolute value of x or having absolute value of negative x is still x. So we can say that f of negative x is the same as 2 times absolute value of x. And because now the result is the same as the initial function, we can say that this function is even, therefore is symmetric about the y-axis. Here we will be done with section 1.1, Review of Functions. Thank you.